All right, let's talk about the conservation of energy. So energy, there's just like everything else, energy has units, and those units are there to help us know how much is there. And the energy we use is called joules, the Joules. It's much like Newton's in force, only we're talking about energy. You say you have joules. Well, how much energy are you packing? Packing 100 joules or 200 joules or whatever it may be. Now we talked about mechanical energy last time with it being our total energy. Okay, it's all our potential added to all our kinetic. And in most cases, it's just going to be a few potentials with the kinetic. And at times it may just be a few potentials, and sometimes it'll be a lot of other stuff. Okay, but we talked about it being the mass times the gravity times the height of the off the ground of that object. And we've talked about this equation, 1/2 times the mass of the object times its velocity squared. Okay, and our spring elastic. Now, let's do a quick example of how to solve for this equation. So Jane, there she is standing on her thing, 52 kilograms is on her high dive. The high dive is 5 meters tall. How much gravitational potential energy does Jane have? Well, if you remember, our equation is gravitational energy is equal to the mass of the object times the acceleration of gravity on that planet times the height. Well, Jane happens to be our object, and she is 52 kilograms, and our mass is in kilograms, which is what we always want it to be in. So 52 times by the acceleration of gravity, since we're on Earth, that's going to be 9.8 times by the height. She is at 5 meters, so that's times 5. You always want this in meters as well. If we do 52 times 9.8 times 5, that is going to equal, if we solve for that, that is equal to 2,548 joules. Okay, that is how much gravitational energy she has. Now, throughout this situation, see how she's kind of in that box on the high dive? Throughout this situation, she is going to have that much. Okay, so here's our kinetic example. As Jimmy, 75 kilograms, watches Jane jump, he gets nervous and runs 5 meters per second towards the edge of the pool to make sure she isn't hurt. How much kinetic energy does Jimmy have? Okay, let's look. Remember, kinetic energy is equal to 1/2 times the mass of the object times its velocity squared. So in this case, Jimmy happens to be our object, so it is going to be 75 is our mass. We have to times that by 1/2 times its velocity squared. Its velocity happens to be 5 meters per second. It's in meters per second. This is exactly what we need it in, times 5 squared. We solve for that, and that comes out to be 937.5 joules. There she goes. Jimmy running to save her. Our spring elastic energy. Okay, so you've got to do some work. Work equals force times distance, so we've got to apply a force to the block, move it a certain distance, and that's going to be our work. Remember, force is just mass times acceleration of the object. How much force does it take to draw back on a bow a small amount? Does it take the same amount of work as if you draw it back all the way? So you realize that just pulling it back a tiny bit doesn't take that much. There's not that much force involved, and there's not that much distance, so there's not as much work. But if you were to pull this bow the entire way back, you realize that it takes a lot of effort. It's being stretched quite a bit, so you have to use quite a bit of force, and its distance was a lot more. So the work that is in this situation is much more than the work in this situation. Okay, there's our equation, potential spring equation. 1/2 kx squared. Okay, remember k was how much the spring constant, so the stronger the spring, the bigger the number, or elastic. So a bigger rubber band is going to have a bigger k than is a smaller rubber band. X is the distance that it was compressed. Let's move myself out of the way. Is the distance that this spring is then compressed. Okay. So let's look at a practice problem with Jane. If Jane can store 435 joules of energy in the ballista spring, how far back will she be able to pull the bowling ball if the spring constant is 7? Okay, so this is an energy problem, and if we want to look at it normally, we can tell that we've got energy here, we've got a number here, and we're trying to figure out what we're solving for. So we know the equation is spring energy is equal to 1/2 kx squared. So right here we have our energy, 435 joules of it. We know our spring constant. There's two variables. We only have one variable left, so this is a solvable problem. Plug in our numbers. 435 equals 1/2 times k, which is 7. We just grab that right out of the problem and put it in, times x squared. Okay, now we just solve for x. Times by 2, times by 2. Those 2's cancel. We get 435 times by 2 is equal to 7x squared. Now divide by 7, divide by 7. Those 7's cancel. We are left, let's draw it right up here, with 435 times 2 divided by 7 equals x squared. Now we just square root. We get 435 times by 2 divided by 7. All of that square rooted equals x. And x we find out to be is 11.14 meters. In other words, Jane's ballista, or her little bowling ball, should be able to be pulled back 11.14 meters. As we see, she launches, she gets Jimmy, and he gets blown away. All right, so we've seen this before, that the conservation of energy, it cannot be created or destroyed. Energy is always there. We can just transfer it from one into another. So in Jane's case, in the previous problem, she had a bunch of stored elastic energy that was then transferred into the energy as form of kinetic and gravitational, since that bowling ball ballista was off the ground. So how does the energy change as a pumpkin falls? Well, if you notice, you have 5 meters, and we're off the ground and we haven't moved yet. So in other words, all of our energy is going to end up being gravitational energy. Right there, we have 1, 2, 3, 4 bars. A little over 4 bars of energy, and it's all gravitational. This means, since we're right here at 4 bars, we have to have 4 bars in this situation, and we have to have 4 bars at the ending situation. Okay, so if we move here, we have cut our height in half. If you cut your height in half, remember the equation, mgh. If our height goes in half, it's also going to cut our energy in half. So we're now going to have half of our energy that we had in this situation. So, and since it's falling, it is now moving, so we have half kinetic, half gravitational. If we would only fall in a meter or so, we'd only have 1/5 of our gravitational energy gone, and 1/5 of it as kinetic. But notice there's 1, 2, 3, 4 bars. 1, 2, 3, 4 bars. They are conserved. Okay, the last situation, notice we're not off the ground at all, so we will not have any gravitational energy. So all the energy happens to be in kinetic. And we're assuming, obviously, this is right before it hits the ground. And even if it does hit the ground, this pumpkin is probably going to shatter, and it will go in all different pieces, which is also still things are moving, that is kinetic energy. Now, we can figure this out number-wise as well. If you look at, we have A, we have B, and we have situation C. We can figure out how much we have. Notice we are moving, and we are off the ground. So we are going to have both kinetic and gravitational energy. We have 1, 2, 3 bars of gravitational and 1, 2 of kinetic. Okay. At this point in time, we've rolled down the hill. We have all kinetic. Notice we are not off the ground at all. So all of this energy was then transferred into here. So that's 1, 2, 3, 4, 5. We should have 5 bars of kinetic. And in fact, we have 1, 2, 3, 4, 5 bars of kinetic energy. And we have the same amount, which means we're going to need 5 bars over here as well in situation C. Okay, now notice we are off the ground, so we do have some gravitational energy. Notice we probably are going to be moving, and so we will have some kinetic. So how do we figure that out? Okay, notice we just have more kinetic than we do gravitational, but once again we have 1, 2, 3, 4, 5 bars as we did here. Now we can figure this out number-wise as well. So how much energy, total energy, does the system start with? Remember, total energy is your mechanical energy, which is all the potential added to all the kinetic. So we need to add up our potential here of gravitational and our kinetic energy. Okay, so 1/2 mv squared is our kinetic plus mgh, which is our gravitational. We found out that we're moving, mass is 800 kilograms. We're moving at 10 meters per second, so we got to square that, plus 800 times 10, rounding 9.8, as with an 80-meter height. You add all that up, 40,000 plus 640,000, you get a total energy of 680,000 joules, which means in situation B, we're going to have 680,000 joules, and in situation C, we're going to have 600,000 joules. This is the conservation of energy. How much kinetic energy does the cart have at point C? We're trying to figure out how much kinetic is here. We know how much kinetic is in B. That's easy. It's 680,000 joules, okay, because all of it's kinetic. But C is going to be a little different. So what we do know is that the total energy, once again, we're just going to use this same equation. The total energy is 680,000. So we're going to put 680,000 in for this number. We know our height. We know gravity is still 10. We know the mass of the object is still 800. So we know mgh. And so really, whatever number this is, that's going to be what's left. Okay? So 600,000 equals our kinetic energy, which is the same as this, plus our mass times our gravity times our height, which is 800 times 10 times 35. We get 680,000 joules equals our kinetic energy plus our gravitational energy, which is 280,000 joules. We minus over 280,000. Our kinetic energy is 400,000 joules. Now, given that it's 400,000 joules, we then could figure out our velocity at this point. We just plug it in for here. We know the mass of the object. We could solve for velocity.